I'm going to move to the next phase, which is to introduce the circulating fluidized beds. Remember, I said when lighter particles or particles, when the gas velocity in the fast bed, okay, exceeds the terminal velocity of these particles, then a large number of them will be lost, but will escape out of the bed. So then, I mean, you have bed material, you have, well, you won't lose bed material, but you have reactants, you have fuel, and all of those, they escape. And more than that, they all carry significant amount of thermal mass with them. So later on, as I mentioned, a circulating fluidized bed concept came in, most replacing most of the bubbling beds. A very simple characterization here. This is the bed, okay? And this is what we call the riser section of this entire CFB unit. We have air passing through here. Forget about the secondary air for now. You have gas and particles, but gas velocity is so high that much of the particles, they are leaving. They are captured by a cyclone here, and of course, gas will have to escape and comes back. And with a given ratio, the fluidization gas will determine that some of the particles will be recirculated back. And therefore, if you're, for example, burning coal, it will then, by this way, you will burn it to almost largest amount, there will be no unburned fuel left. So it is a gas solid contacting device, nevertheless, many industrial applications. Hydrodynamics of a CFB is much more complex than the bubbling one. And it will be the geometry of the riser, particle properties, and adding to that is the secondary fluidization gas. Why do we need a secondary air injection? We will explain it later, but just this alone, if you use this, you'll end up with lots of slugs because this air alone is not in a large vessel good enough to give you the ideal mixing environment. So therefore, you need a secondary air injection. Um, I will further explain this when we uh, apply it to combustor. Um, Very attractive technology, as I said, when oil became very expensive and very difficult to find. Most utilities were using coal, of course, a lot cheaper and a lot more abundant. And then CFBs all of a sudden gave us much higher combustion efficiency, but more importantly, much better emission control. We will cover this extensively later on when we do fluidized bed combustion, but you should understand that this is the reason why CFB is the reason why we are able to do this. Now, here's the example of a CFB for a combustion application. You have fuel plus sorbent here. You know what sorbent is. In this case, they are calcium carbonate particles, for example, to capture sulfur dioxide or sulfur oxides mostly. But let's leave it aside. They enter, you have the primary air, you have the secondary air. Secondary air could be in the form of like, oh, tangential swirl or in the form of radial injection. There you will see which one is best. Then you have reactions taking place here. In this case, of course, combustion. You have particles burning as they're burning. Air is hot, particles are hot. You put heat transfer surfaces here. that transfer the thermal energy of hot air and particles into the working fluid here. They all escape, captured by cyclone. Of course, air goes out. This air is further utilized later on, but we'll leave it alone. For now, particles come back. We call this area standpipe, and particles are reintroduced into bed. Of course, you can't keep doing this and add new particles here. Part of the ash, whatever particles, will be taken out here. It's all under control by adjusting this aeration. Okay, so this is the principle behind a circulating fluidized bed. Okay, remember, a bubbling fluidized bed is a once operation. Bubble reaction takes place, and whatever the reactants are, they leave, and you add more, either continuous operation or batch operation. In bubbling fluidized beds, bubbles are present. In circulating fluidized bed, it's a continuous operation. It's not a one-time operation. Continuously fuel and whatever sorbent they're fed, and there are no bubbles. Okay, it is in fast fluidization mode and no more bubbles in this mode. So big difference. It changes the entire, of course, changing the hydrodynamics. You change the heat transfer and mass transfer. In a circulating fluidized bed, both of them are much, much higher. So this is, if you cut this right there, you will see that membrane tube wall. This is the wall insulated. You have heat transfer tubes or extended fin surfaces, and this is where suspension, hot gas particles, and all of those are. Or you can refractory line all of these. So I want you to think for a second, okay? Uh, why, for example, we add this refractory line wall. Heat transfer tubes, they are tubes. They're always like metal, okay? Metal tubes. The particles, the bed part of sand, for example, ash, sand, all of those, and they are all very hot, abrasive, and are moving at very high velocities. So can you imagine every second, hundreds, thousands of these bombarding these surfaces? What will happen? After a while, these surfaces will get weaken. It will eat up the wall thickness, and after a while, your heat transfer tubes will fail, and the working medium, whatever water, steam, start escaping. And imagine this is a 160 megawatt electric boiler, and then you'll have to shut it down, and it will take months and months to repair. So to avoid that, you put a refractory lining. Of course, heat transfer will be hampered here, but nevertheless, it is a good thing to do. Otherwise, again, erosion will damage heat transfer surfaces. Again, heat transfer is a lot more complex here. You have to take convection, conduction, and radiation all into consideration to do this. So I showed you the schematic for the bubbling fluidized beds. Uh, it looked very complex. In CFBs, it's a lot more complex. So at high velocities, these individual particles will tend to come together, cluster. This is it's a natural phenomenon. It's called the minimization of energy principle. Okay, that when they do that, uh, it will be a reduced drag force on them. This is why you have the school of fish or flock of birds flying in formation to minimize the drag force. Particles, the same. When they do that, they form a cluster, and the drag coefficient of this cluster, let's say if you have 100 particles in this cluster, the total drag force is smaller than the drag force on one summation of a drag force on 100 individual particles, okay, because of internal circulation within these clusters. But nevertheless, we don't know the size, we don't know the shape, we don't know the number of particles. Therefore, how much heat they will carry and pass it on the wall or heat transfer surfaces is all correlations, and we'll have to rely on a lot of experiments. Later on, we can build some models that will give us, especially with verification with experimental numbers, much closer values. But this should give you an idea about red shows, of course, higher temperature. Yellow is cool down because they are given their high thermal energy to the cooler walls. Okay. So we covered these mostly. We covered these parts, and we mentioned that hydrodynamics have direct effect on these things. So let's talk about then the mixing of gases. Okay, since in CFBs we said the bubbles are no longer present. Okay, we kind of broke all of them down. Okay, and they are now present in the scale of eddies. Gas turbulence scale is 0.1 of tenth of the vessel size. Okay, so when you think of this rectangular shaped vessel or cylindrical, but however cross section, and you have gas flow upwards, it will have diffusion to the walls. Okay, this is the diffusive effect, but also due to turbulence effect, so that you will have mixing of gases, radial mixing, and of course that in turn, this air gas movement will affect the particles movement across the cross section. Okay, so it is very important. This is one of the most critical parts of designing. Otherwise, you won't get the benefit of using the entire geometry of your reactor. Okay, if you don't have proper mixing in it. And furthermore, if you don't have proper mixing in it, you will not fully utilize all the reactants. For example, if you have fuel, let's say coal particles, and if you have air, you don't get to burn all of this. A lot of it are escaping unreacted. So this mixing is very, very important. Make sure that you have this. So you think of a furnace, a boiler, and I'll give you some dimensions, okay? A cross section of 2 meters by 3 meters, okay? And in there, you blow air from underneath. regardless of how well you design your distributor plate, you will not be able to achieve uniform distribution that will give you this mixing. Okay. And if you don't have that uniform distribution, as I said, you will not be achieving your high heat and mass transfer rate. For that, I'll go back here for a second. We use a secondary air injected into the air here to provide us with amount of air. There is a lot of stoichiometry involved as well, but I won't get into that. But as for the mixing, we can use either introduce this tangential swirl injection, radial injection, or mixed of it, so that it will give uh, additional mixing of air that will enhance both heat transfer and mass transfer. So this thing started years ago when they had one of the first boilers. A lot of when gas sampling was being made here, right around here, they were measuring a lot of carbon monoxide, presence of carbon monoxide. And the reason for that was that that showed that all the fuel was not reacting. Okay, it should have been much less carbon monoxide, a lot of carbon dioxide, whereas the ratio was much higher here. That necessitated blowing more air here, provide more air, therefore you increase the excess air ratio, but more importantly, to promote that mixing here. So, um, did a lot of these measurements in my lab years ago, and we to find the optimal swirl element to give us the maximum amount of mixing. So the red dots, the curve, um, is at Z shows the elevation, so elevation above the secondary air injection. This is empty riser. There are no solids in there. I wanted to see how this just using the secondary air will influence mixing. So this is the dimensionless radius. This is the concentration. Um, you see how this distribution, this is very bad, right? Very poor here, a lot of it concentrated here. Go a little higher, it's much better. And another level, you see much better distribution. That shows that mixing is very successful as you go further up. But we don't want, as I said, the higher the height of the reactor, the more money you have to spend on building it. So we don't want to just make it too tall. So we then start injecting air with solids. This is when there is no secondary air injection. You see again how pointy it is. Then you start at a certain ratio, tangential. It's represented by blue. Radial is the best mixing, and the mixed one is here. So for this specific application, you could see how important it is to design proper secondary air injector. Now, we won't have time to go through this. This is an entirely different area. But those of you who may be knowledgeable, because I honestly don't know your backgrounds. I don't know whether you're practicing engineers. I don't know whether you're graduate students. I don't know. But computational methods, models, especially in recent years with the advance of high capacity computation, enabled us to predict the turbulent behavior under multi-phase reacting conditions much better. So I'm just going to fly through this very quickly. Um, basically, we use either Eulerian continuum model that observer is stationary, or Lagrangian observer moves, or a mixture of both. And we did this successfully, and you can see that we can predict solid concentrations both longitudinally and horizontally in various geometries. So various, again, you can use your Eulerian means, why am I repeating that? Eulerian Lagrangian. One is for the gas phase, the other one is for the solid phase or particle phase. And using those will give us very good prediction. Again, you have to go through the governing equations, momentum, mass, transfer, and but again, those of you who are interested, you can oops. Let me stop sharing for a second and see if anybody has any comments, any questions before I then start the liquid or solid beds. Any questions? I should mention that this is not my preferred way of teaching learning, because I wish I were there physically and we were having a conversation and we were interacting much better. But nevertheless, if anybody has any questions, am I going too fast? Am I going too slow? However you want to see, or any questions, happy to answer. If not, let's catch our breath for a few minutes and then we'll start the second part. So there are a lot of similarities between what I covered so far for gas solid and liquid solid fluidized beds. However, the applications, of course, they are very different, and therefore it's good to understand a little bit of the basic principles and fundamentals of liquid solid. Basically, in this case, again, for it to be called a fluidized bed, the solid particles must be suspended and in an environment where uh, it will create a fluid-like behavior and it will obey all the hydrostatic laws that are present in that environment. And transition from fixed to fluidized state, just like in the gas solid one, will depend on the liquid velocity and particle properties. Um, what are the applications? In this case, uh, for example, wastewater treatment. It is very natural for wastewater treatment because water is present. It is the water that is a wastewater and it needs to be treated. And therefore, that treatment is through various particles and agents that will help doing this. Biochemical processing is especially in applications where protein recovery is required. And of course, food and pharmaceutical industries where you have to have a very good mixing environment of liquid and particulates. So for those kind of applications, liquid solid fluidization is ideal. Again, uh, you can by using certain agents and catalysts, we can remove phenols from wastewater, which is very much present, or the removal of proteins from cheese whey. Um, we, as will be in all cases, it will improve if we understand the hydrodynamics well and if we design it accordingly well. It will improve a reactor efficiency and to operate these, they're they demand energy, but if it is designed properly, then it will minimize energy consumption and it will enhance heat transfer and mass transfer rates. There's again, just like in gas solid, interaction is very much. Um, I showed you this earlier, but it's again uh, it the same regime in the liquid case. You can have smooth fluidization that you have pretty good dense uniform distribution of particles. Okay, so if you are trying to, let's say, very simple, you're trying to make a smoothie, for example, like continuous operation production, you have your milk or whatever you want, and you want to add a bunch of other stuff in it. And if you're in this environment, you have a very good uniform distribution of it in this environment. Or you want to transport this through long distances. And again, through this, it's a lot faster and economical to be in this environment. Um, it's again, as I said, this technology, similar, parallel to the gas solid. It was founded through various applications that necessitated a better understanding of hydrodynamics in these environments, predominantly by process industries as opposed to energy industries. Um, so these are, I mentioned, key benefits, high interface contact efficiency. It's very important. So if I'm treating wastewater, I am introducing agents, solid agents for that recovery to remove phenols probably. So the higher the contact efficiency, interface contact efficiency, the more economical it is, or much less agents I need to use. The more agent I use, the more expensive it will get. Um, and of course, in this way, we are able to handle larger. So let me pass these, okay? So just for a second, again, liquid, solid, fluidized bed, some of, again, further application by chemical processes. I mentioned this, all of these that uh, you already know. Key hydrodynamic parameters, exactly the same as described: minimum fluidization velocity, dependence on particles, and all of those. The only reason why I'm showing you this, of course, in this case, when you are calculating minimum fluidization velocity, you cannot ignore the buoyancy force. You'll do this, and best thing is to use Erdogan's equation to predict that. Bed expansion is a lot easier to calculate here because of course, incompressibility of liquid. It will expand as it's fluidized. These are same as I mentioned before. Terminal velocity is calculated this way, and you know the significance of terminal velocity because if the liquid velocity exceeds that, it will carry all these particles over. This is again, we use this one. So Two types are possible, and I think you will see the inverse one later on. So if the fluid motion, liquid motion is upward, and if you're using particles that are denser than the fluid, okay, the particle motion is here in this direction, fluid is upward. This is the upward liquid solid fluidized bed. Okay, fluid motion is this way, and part gravitational force is in this way because the particle is density is larger than the liquid density. Inverse fluidized bed, inverse liquid solid fluidized bed. In this case, the fluid direction of the flow is downward, and in this case, the particles are lighter. Okay, so liquid flows downward, fluidizing lighter particles upward. Used for different operations. So, what are the characteristics? Um, if it's inverse, it operates with particles that are less dense than the fluid, provides unique hydrodynamic behavior suitable for specific applications, and of course, upward one is the opposite and more suitable for CFB type of liquid. Okay. Here is again a summary of between the two, because depending on the application and depending on the density of particles and density of the fluid, mostly let's say wastewater, we can assume it to be water density, but it will help you determine whether it both should be upward or inverse. So this is an important consideration. We will, this is basically, it shows us the operating regime under which we will operate the fluidized bed. This is the dimensionless particle diameter, okay? And this is the dimensionless liquid velocity. With doing that, we will be able to extract it much, much better. Uh, Here, this is the fixed bed regime corresponding to certain velocities up to here that you could use a velocity here corresponding to minimum fluidization if you have the right dimensionless particle diameter. Then in this corridor, you run a conventional fluidization regime, okay? That the bed is suspended and it's in the form that I showed you before. Of course, needless to say, in this case, we're not talking about bubbles. It's all incipient, okay? And it's all uniform, but nevertheless, it's conventional fluid bed. Then let's go here and see. So fixed bed, it's stationary, conventional fluidized bed, and minimum fluidization you achieve. Then it's a conventional fluid bed, and then you go above the terminal velocity. Then you're in the circulating fluidization regime. Okay, and where this is the area where a lot of the commercial applications take place. Okay, again, most commonly is the wastewater, and this is above that is in the transport regime. This shows different solid circulation rates. So you have as I said, you're able to adjust the solid circulation rate. The higher the solid for to achieve higher solid circulation rate, you have to have higher fluid velocity. What does it mean? You'll be able to process much higher volumes, okay, quantities. So it's a very important map. It is basically developed using various geometries, different particle sizes and velocities, but this is one of the key design graphs that you want to design a system. Uh, I showed you these. This is uh, at this height, you have fixed bed. Bed expansion is flat. When it's fluidized, of course, bed expansion rises until you reach the terminal velocity and you start removing the particles. Then bed expansion stops. These are all summarized in different regimes. I think we covered all of these under the gas ones. Uh, for the design of a liquid solid fluidized bed system, again, uh, you need to determine the minimum fluidization velocity. You need to have, in this case, if your wastewater it is laden with a lot of solid particulates, and those solid particulates are also interacting with catalysts or other particulates, then you need to determine the overall bulk density and uh, that expansion, you need to figure it out. Solids hold up, you need to figure out so that you can successfully calculate your mass transfer in this case. Um, solid distribution again, mostly it's uniform distribution. You have to have a very bad design to have non-uniform distribution of these particles. I'm going to stop here. It is, as I said, this was much faster than the first part because a lot of the basic principles were the same. And I'm gonna come back here and see if there are any questions.
Good evening, sir. Sir, how do particle properties like size, density, shape affect fluidization behavior?
Hmm. So to particle size will determine, so if we're, let's say particle size of the bed, okay? I'm using sand particles in a bed, or I don't need to use sand particles. If this is a combustion operation, I can use ash particles. I will start it with sand, and then gradually, as I burn more, ash will replace sand particles as bad material. It is very important because particle size will determine the momentum transfer. Particle size will determine heat transfer because if there's a difference between 10 200 micron size particles touching a heat transfer surface, then 1000 20 micron diameter particle size touching because of the as I said, this is the contact point. This is it's only touches here. The smaller they are, the higher the surface contact area. Therefore, it is very important to figure out the right particle size, which also will be effective in its interaction with bubbles. So to do the right particle size, you have to go through a particle size analysis and find the right statistical diameter of the particles because they're all of different sizes, different shapes.
Thank you, sir.
Okay. I am, unfortunately, I'm recovering, as I mentioned, from illness, and it's very late for me. If there are no other questions, I'm going to sign off, and then we can regroup again tomorrow at the same time and then go over combustion.